Hello everyone! This video is entitled Electron Configuration. In this video, I will teach an abbreviated means of writing out electron information. This abbreviated method is a shortcut to writing out the quantum numbers for an element, while still retaining all the relevant information. If you've not yet watched my video on quantum theory, it is recommended that you do so first to fully understand this material. You can find a link to that video in the description below. Okay, let's get started.
So quantum numbers are an incredibly useful tool. However, they can also be arduous things to work with. So say we're talking about an element like uranium. If we wanted to write out the quantum numbers for uranium, which has 92 electrons, I would have to write out 4 separate quantum numbers for each one of those electrons. And that would occupy a minimum of 92 separate lines. And so chemists have developed a shortcut to writing out that information. We call that shortcut electron configuration. Now this notation is comprised of 3 separate parts. The first would be the principal quantum number, the n value, so the energy level relating to a specific sublevel. The next would be the sublevel type, or the orbital type. So in hydrogen's case, we have energy level 1, and we have an s orbital, and so we signify that by 1s. The last component is the number of electrons in that specific subshell. So in hydrogen's case, we only have 1 electron, and that 1 electron exists in the s orbital, and so we write it as 1s superscript 1. In the case of helium, the ground state electron configuration would be 1s2. And so 2 would be the superscript indicating the 2 electrons that are filling the s orbital. For a lithium atom, the electron configuration would be 1s2, 2s1. Let's use this image to review where the s, p, d, and f blocks are located on the periodic table. So of course the s block is going to be located in groups 1 and 2, and of course you have helium all the way here in group 18 as an exception. The p block is going to be located between groups 13 and 18. The d block between 3 and 12. And of course the f block is actually sandwiched between the d block and the s block in periods 6 and 7. When it comes to electron configuration, I find it's best to explain things with the use of examples. Here are some practice questions that may help you grasp this notation a little better. So helium. How do I write the electron configuration for helium? Well, the very first thing I'm going to do is I'm going to consult the periodic table. So helium is in group 18, period 1. The period number identifies the energy level helium is in. So period 1, energy level 1. It has 2 electrons. So how do I write out the electron configuration? Well, I need to know what orbital type helium is in before I can move on. And so I know that helium is actually going to be an s-type. I know this from the last slide. Helium is the only exception that is located outside of group 1 and 2 that happens to be part of the s block. And so putting it together, it'll be written as 1s2. 1 being the energy level, s being the orbital type, and 2 the number of electrons that are allocated for that s-type orbital. So lithium. Let's attempt to do the same for lithium. To locate lithium, we find it here. It's in group 1, period 2. Period 2 indicates that it's in energy level 2. However, lithium has 3 electrons. So how do we allocate those 3 electrons? Well, we must remember that the electrons first must fill the energy levels closest to the nucleus. So the energy levels that are lower, we know that there's only 1 orbital that is lower. That is the 1s orbital. And so that 1s orbital will take 2 electrons. 1 electron will be left to be placed in the second energy level. What is the orbital type in the second energy level? Well, it will be an s-type because lithium is in group 1 and 2, which is the s block. So let's put it together. Lithium will be 1s2, 2s1. Let's do the same for beryllium. Beryllium happens to be located right beside lithium. Now it has 4 electrons, and again, those electrons will be allocated very similarly. Two of those electrons are going to go to the lower energy orbital. There's only one, so it'll be in the 1s orbital. And the two remaining will be used to fill the s orbital in the second energy level. And so we write it out as 1s2, 2s2. Let's move on to oxygen. Oxygen is also in the second energy level. It is in group 16. It has 8 electrons. Now, what's important to note is that oxygen is in the p orbitals, or in the p block, but in the second energy level. Now, although we have 3 p orbitals, those p orbitals can in fact hold 6 electrons. And so, how do we allocate those 8 electrons? Well, 2 of them are going to go to the 1s orbital. 2 of them are going to go to the 2s orbitals. Again, those are lower energy level orbitals, and so those must be filled first, leaving behind 4 electrons. And those 4 electrons will be located in the p orbitals. Remember, the p orbitals can hold as many as 6. And so when writing out the electron configuration, it will look like this: 1s2, 2s2, 2p4. Now I must note, those numbers are superscripts. You must write them as superscripts. You cannot just write them as coefficients beside the letters. It would be considered incorrect. Let's move on to chlorine. Chlorine is also located in the p block, but this time for the third energy level. So it's the same pattern that applies. We must fill the lower energy level first. So we will have 2 electrons in the 1s orbital, 2 electrons in the 2s orbitals. The 2p orbitals will now be filled, 2p6. We'll have 2 electrons allocated to the 3s orbitals, and the remainder, which will be 5, will be placed in the p orbitals for the third energy level. And so we write it out as 1s2, 2s2, 2p6, 3s2, 3p5. And finally, we'll move on to calcium. So calcium is in the s block, but for the 4th energy level. So in fact, if you think about it, it'll be the exact same thing as chlorine, but instead of being 5 electrons in the 3p orbitals, it'll be 6. And we just place 2 more electrons in the s orbitals for the 4th energy level. And so it will look like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. These practice questions work in reverse. Here I've given you the electron configurations, and I'm asking you to identify which element those electron configurations refer to. In fact, these questions actually are easier than the questions we just completed, because in this situation, you really only need to look at the last input for the series that is written. So here we have 3p1. 3p1 is the location of the element we're referring to. So let's try to locate that. So 3 meaning third energy level, p meaning p block, okay? And 1 is the first electron in that p block. Remember, there are 3 p orbitals, but 6 possible electrons. Each one of those electrons represents a different element, hence why you have 6 separate slots for the p block. 1, 2, 3, 4, 5, 6. So if it says 3p1, we know it's referring to the very first element in that p block, and this would be aluminum. The next, well, we're looking for 3p3, so the third element in the 3p orbitals. So third energy level, p block, 1, 2, 3, that element is phosphorus. Now we're looking for 3p6. So same thing, third energy level, 1, 2, 3, 4, 5, 6. That element is argon. For the 4th question, 2p3. Let's move to now the second energy level, and we are looking for the third electron in that p orbital, so boron, carbon, nitrogen. And lastly, for the fifth question, 3D2. Here, it's asking us to look in the D block. And so, third energy level. Oh, where is the D block? You must remember that the D block actually comes after the 4s orbitals. And so the D block is actually located between element 21 and element 30. It's asking us for the second element in the D block, so that would be titanium. Now that we know how to write out the electron configurations for elements, on this slide, for example, we have the electron configuration for boron. We must also know that chemists use what are called orbital diagrams alongside these electron configurations to keep track of electrons. Orbital diagrams are more visual aids to the allocation of electrons. And so orbital diagrams are written as these small little boxes. And this box can be empty, which would imply that it's unoccupied, meaning it could be filled with electrons. It could have one electron pointing upward. That would mean that you have a positive spin electron and it's half filled. It could be pointing down, meaning that you have a negative spin electron and also that orbital is half filled. Or you can have a box with two electrons pointing in opposite directions, meaning that you have a filled orbital with positive and negative spin electrons. This slide will help us make sense of the energy level discrepancies that seem to be counterintuitive on the periodic table. What I mean by that is the increase in energy level for different types of orbitals. 1s is lower in energy than 2s. We know that showed on the periodic table. 2p is slightly higher, followed by 3s, followed by 3p. Now, it would make sense that the 3p orbitals would be followed by the 3d orbitals. However, 4s orbitals are actually slightly higher in energy than the 3p orbitals, but actually, if you take a look, are lower in energy than the 3d orbitals. And so that's why the 3d orbitals follow the 4s orbitals in energy level in the periodic table. Now, it gets interesting as you go higher. 3d is followed by 4p. 4p by 5s. But 5s is actually followed by 4d, not 5p. 4d followed by 5p is then followed by 6s. But this is where it gets really interesting. The 6s orbitals are actually followed by the 4f orbitals. Now, the 4f orbitals are just ever so slightly higher in energy. And so that's why you need to write 4d, 5p, 6s before you can arrive at 4f. So to sum up, these diagrams show the total number of orbitals you can have for electrons to occupy. They're represented by boxes and are listed in increasing order. And different orbitals have different relative energies. But the most important thing to remember is that energy levels must be filled with electron in this particular order. You must fill electron orbitals in the order of increasing energy. The Aufbau Principle. Aufbau, meaning building up in German, is meant to allude to the building up of energy within orbitals. The Aufbau Principle takes these orbitals and organizes them by increasing energy. Scientists use this principle to know exactly which orbital they need to fill first before moving on to the next. The Aufbau Principle was actually proposed by Niels Bohr sometime in the early 1920s among the advancements in quantum mechanics. It's because of the Aufbau Principle that we know, for example, that the d orbitals in the third energy level must be filled after the s orbitals in the fourth energy level. And this is, of course, because of the varying degrees in energy. At the bottom of the slide here, you can see that I've taken this image on the right and delineated it into a single line for your reference. What this shows you is the exact order of orbitals that you must fill first before moving on. This image on the right is actually very useful for students. Many students will use it during their homework sessions, and a lot of students will actually take it and write it onto their quizzes or tests as something to quickly refer to. It's very easy to do. Essentially what you do is you write 1s all the way to 7s, 2p all the way to 7p, 3d to 7d, 4f to 7f. And using a ruler, you draw these diagonal lines that intersect so that you can exactly identify which orbital and which sublevel must be filled first before moving on. So for example, 3d would be followed by 4p, which is followed by 5s, which is then followed by 4d. Now I know I covered Hund's rule in the last lecture, but I'm going to review it here to reinforce how important it is and how relevant it is to the material we're learning today. So Hund basically stated two very simple things. He stated that every energy sublevel must receive one electron first before any one of those orbitals in that sublevel could be paired with a second electron. He also stated that every electron that goes into an orbital to half fill that orbital must be the same spin as the orbital next door to it. And so if you take a look at the p orbitals for nitrogen, every single one of them has received one electron, and every electron that has been received has a positive spin. Those positive spin electrons will then be paired with negative spin electrons, each individually in order. This slide shows Hund's rule in action. If you take a look at boron, boron has one electron in its 2p orbitals with a positive spin. Carbon receives a second electron in its 2p orbitals, also with a positive spin. Nitrogen, a third electron, again a positive spin. It's only when you get to oxygen that you start to pair up these orbitals with negative spin electrons. And so oxygen has one electron with a negative spin in its first p orbital. Fluorine, a second negative spin electron in its second p orbital. And neon, a third, completing the set, filling the 2p orbitals with 6 electrons. Now that you know how to use electron configuration notation and orbital diagrams, it's important that we discuss what are called exceptions. Now, by exceptions, I don't mean that scientists have found a way to make a theory that shouldn't work apply to the natural world. No, this is not an example of a rectangular peg being placed into a circular hole. Instead, what we found through our experimental evidence is that certain atoms will actually arrange their electrons in a way that is more stable than the theory predicted. Chromium is one such example. Chromium is more stable when its 4s orbital donates an electron to the 3d orbitals so that both sets of orbitals are actually half filled. Now, this is actually supported by the Pauli exclusion principle. The Pauli exclusion principle outlined 3 possibilities for stability. The first was that the whole orbital set could be filled with electrons. That makes sense. The second was an orbital set that is half filled, and the third, an orbital set that is empty. And so here, the chromium atom has found more stability in having 2 half-filled orbital sets instead of one filled one and one partially filled orbital set, the partially filled d orbitals. Copper is another example. So copper, instead of having a filled s orbital and an almost entirely filled d orbital, its 4th energy level, s orbital, is half filled, and the d orbitals are now filled. This is a far more stable configuration for the electrons that allows copper to be as stable as we know it to be in the natural world. This slide provides a great visual for the exceptions we just discussed. Highlighted in yellow are the exceptions chromium and copper. Now for chromium, you have 1 electron in the 4s orbital, and you have 5 electrons in the 3d orbitals. What you should have is 2 electrons in the 4s and 4 electrons in the 3ds. What chromium has done here, and I know I'm anthropomorphizing chromium, I'm attributing human characteristics to the atom. Obviously, the atom has chosen nothing. Okay, what's happened is a consequence of magnetic and electric fields. What occurred is that an electron essentially moved from the 4s orbital to the 3d orbitals. And this is a far more stable orientation of electrons. The reason being is the 4s orbital is a lower energy orbital. Now, although it would have been filled and stable, it would have left behind 3 d orbitals that are so close to being half-filled. And in fact, there is this amazing idea in quantum mechanics where you can have very stable orientations with electrons in only 3 different categories. If the orbitals are empty, it's very stable. If the orbitals are half-filled, it's very stable. And of course, if the orbitals are filled, it's very stable. But it's unstable if you have what's called partially filled orbitals. So if you're very close to being half-filled, or if you're very close to being filled, it creates a very lopsided magnetic field, a very unstable atom. And so what chromium has done is it's moved 1 electron from its 4s orbital into its 3d orbital, which is a higher energy level, creating 2 types of orbitals that are half-filled instead of 1 orbital that's filled and another set that is partially filled. Copper did something very similar. So copper would have been partially filled and very close to being filled in its d orbitals. So it would have had, instead of 10, it would have had 9 electrons in its 3d orbitals. And so what copper has done is it's moved 1 electron from its 4s into its 3d. And what we have now is a half-filled, stable, or as stable as we can get with this atom, 4s orbital, and a full higher energy 3d orbital set. This table shows a selection of the main exceptions to the Aufbau principle on the periodic table. Although there are other exceptions, especially around the F block where it can get quite complicated, these exceptions are the ones that you are expected to know. Now, of course, we've already discussed copper and chromium, but just like copper, silver and gold are very similar in their exception. 1 electron was moved from the s orbital in the 5th energy level to the d orbitals in the 4th energy level to fill those d orbitals and half-fill the s orbitals. Similarly, gold has moved 1 electron from its 6s orbitals to its 5d orbitals. Molybdenum is very similar to chromium, where it moved 1 electron from its 5s to its 4d, so that both of those orbital types are half-filled. Now, palladium is the picture of stability. What palladium has done is, instead of moving an electron from its s orbital into its d orbitals, what it's done is it's moved both electrons from the s orbital to the d orbitals and eliminated the 5th energy level altogether. Now, this is a move that stabilizes the atom greatly. That idea in quantum mechanics, where an orbital set or an orbital can be stable if it's filled, half-filled, or empty, not only applies to orbitals, but it also applies to energy levels. And so imagine energy level 5. Energy level 5 can hold a slew of electrons. But in this case, it only has 2 electrons in the entire energy level. In the predicted ground state electron configuration for palladium, it only has 2 electrons in the entire energy level. And that makes that entire energy level very, very partially filled, which is incredibly unstable. So not only is the predicted electron configuration unstable because the 4d orbitals are partially filled, very close to being filled, but the 5th energy level for palladium is very partially filled. And so what this atom has done is it's moved both electrons from the 5th energy level and the s orbital into the higher energy level 4d state, giving you a full 4d energy level. And I know that you might be thinking, well, the s orbital is filled. Why would it remove both electrons? Why wouldn't it just make it a half-filled s orbital in the 5th energy level? Well, again, you got to think about it. The d orbitals would then only have 9 electrons, so it would still be partially filled. And you would still have a now even more partially filled 5th energy level. And so moving both electrons from the 5th s orbital to the 4d orbitals stabilizes this atom greatly, and that's why palladium is so stable. Here we're going to discuss the formation of ions, the creation of cations and anions by the loss and gain of electrons, and how that relates to electron configuration. So the example I have here is aluminum. Now, aluminum has a charge of 3 positive, but why does it have a charge of 3 positive? Why does it continue to lose electrons until it reaches a 3 positive state? Let's take a look at the ground state to explain this to us. The ground state has 3 electrons in the third energy level. Now, the third energy level has the potential of holding 18 electrons, 2 in the s orbital, 6 in the p orbital, and 10 in the d orbital. So a total of 18. But instead of having 18, aluminum has 3. So the entire third energy level is very partially filled. And like I said in the last slide, palladium lost the electrons in the fifth energy level so that it could stabilize the entire atom. Why have a partially filled energy level altogether if you can remove it and have a stable, filled set of energy levels and orbitals? And so if you look at the ionized state of aluminum, the ionized state of aluminum has gotten rid of the third energy level altogether. And if you recognize, that ionized state is very similar in electron configuration to that of neon, which is a noble gas, very, very stable. And so by looking at the other possible charges that aluminum could have, it makes it very clear why it settles on a 3 positive charge. And so aluminum positive 1, you can see, has gotten rid of 1 electron, the electron that occupies the p orbital, and it has created a 3s2 orbital state. Now, this to a lot of students looks very stable. You're thinking, okay, the s orbital in the third energy level is filled, and so are all the other orbitals beneath them in energy. And so why would it continue to lose electrons? Again, very important to not only think of the orbitals, but to think of the energy level. If aluminum were to keep the 2 electrons in the s orbital for the third energy level, it would essentially also be keeping an energy level that is incredibly partially filled. So yes, the orbital is filled, but the energy level is not. It's nowhere near the half-filled or filled state, but it is incredibly near the empty state. And remember, those 3 states are what are stable. If the orbital or energy level is filled, half-filled, or empty, you have a state that is stable. And so it gets rid of those 2 electrons to land on a 3 positive charge. So let's look at some practice questions to clarify and solidify this concept. So chromium. Before we move on, I'm going to draw your attention to the abbreviation I actually have here. And yes, what I've done here is I've abbreviated the abbreviation. So electron configuration is an abbreviation to quantum numbers, but you can further abbreviate electron configuration by essentially putting in brackets the noble gas that precedes the element that you're discussing. So here we have the electron configurations for chromium. Now, argon is the noble gas that comes in the line prior to the placement of chromium. What you can do to abbreviate the electron configuration of chromium is to take argon, which is the previous noble gas, put it in brackets instead of writing all of the electron configurations for argon, and then just writing the electron configurations that occur after argon to get to chromium. And so argon 4s1 3d5 is the electron configuration for chromium, like we just saw. And this is its ionized state. So what it's done is it's gotten rid of the 4s1 and 2 electrons from the d orbitals and leaving behind 3d3. Now, I know what you're thinking. You're thinking, well, that's not stable. It was stable with 3d5. Now it is partially stable in its d orbitals. Well, you always have to keep in mind that the ion is also forming a bond with a counterpoint, another ion, and that secondary ion that's coming in is going to stabilize those d orbitals. So unlike the aluminum example where you can have a very, very stable electron configuration as an ion, it is possible to have what looks like an unstable electron configuration for an ion, bearing in mind that that ion is obviously going to form a bond with another. Now let's take a look at iron. So this is the electron configuration for iron. And what I've chosen to do here is I've chosen not to abbreviate the electron configuration for iron, but of course you could. Now, what is the ion going to look like? What is the electron configuration for iron 3 positive? I'm hoping you've caught it here. So essentially what iron has done is it's removed the s orbital altogether for the fourth energy level, and it's removed one electron from the d orbital. And so unlike the chromium ion, the iron ion is incredibly stable in its configuration, and that's probably why we see so much iron in the planets that we analyze. And it's because it's such a stable ion. It really just forms bonds very, very well, and very strong bonds. And it's because of the strong configuration that it has in its electrons. And so it removed the fourth energy level by removing the s orbital, and it stabilized the d orbitals. And of course, it can bond from there. Let's look at sulfur. This is its ground state electron configuration, and this is what it looks like as an ion. So it's gained 2 electrons, and it's placed it into its p orbitals. And of course, the p orbitals are filled with 6 electrons, and so it's filled its p orbitals altogether. And that stabilizes sulfur very, very well. Here I'm going to explain the electron configuration of multivalent elements, elements that can have more than one ion form, by comparing a multivalent element to an element that is monovalent. And so cadmium, this is the electron configuration of the element before it ionizes. And looking at it, some students might think, oh, okay, yeah, it looks stable. Why would it lose electrons? But again, remember, it has 2 electrons in the 5th energy level. Although it has 2 electrons filling the s orbital, the 5th energy level is unstable. So it's going to lose those 2 electrons, and it's going to have a 2 positive charge, leaving behind an electron configuration of this, just leaving behind the 4d10 electrons. If you look at lead, lead can have 2 possible charges. So it can have a 2 positive charge or a 4 positive charge. This is the electron configuration of the atom before it ionizes. Now, I hope you can see where it's going to lose the electrons. Let's jump directly to the 2 positive charge. So what it's done is it's lost the very unstable 6p2 electrons. And so not only is the 6th energy level unstable because it's unfilled, but it also had 2 electrons that were partially filling the p orbitals in the 6th energy level. So it lost those 2 electrons, giving a relatively stable, not as stable as a 4 positive, but a relatively stable 2 positive charge. But of course, the most stable charge for lead is its 4 positive charge. And so what it's lost is now the other 2 electrons in the 6th energy level. It's lost the 2 s electrons. And so it leaves behind a configuration that has no electrons in the 6th energy level altogether, making the atom incredibly stable. And in fact, that is why the 4 positive charge is the primary charge for lead, because it is the most stable charge. Isoelectronic electron configurations. Isoelectronic refers to the existence of 2 or more atoms and ions that have the exact same electron configurations. What we've described up to this point is the loss or gain of electrons by atoms to form new electron configurations in their ionized state that are more stable than the electron configurations in their atomic state. Here what's being described is the loss or gain of electrons to form ions with new electron configurations, but electron configurations that match an electron configuration of an atom that's stable. There are very few atoms that are stable on the periodic table. These are noble gases. Here you can see the electron configuration of neon, a noble gas. This electron configuration is very stable, and it is the electron configuration of an atom. To the right and to the left of neon, you can see examples of elements that have ionized so that they can have matching electron configurations to this particular atom, so that they can become stable as well. We call this type of occurrence an isoelectronic series, where these species have exactly 10 electrons that match this particular atom. And of course, the same can be said of other noble gases that have elements which have ionized to match their electronic configurations. And with this definition, I conclude this lecture. I hope that everybody has understood the material and have enjoyed this lecture. All the best.